In this video, we are going to look at a wireless security protocol called WEP, which stands for Wired Equivalent Privacy. So this was the earliest protocol used in wireless network in the late 1990 and early 2000. So the purpose of this protocol was to provide a Ethernet-like environment in the wireless setting. What that means here is that for STAs belonging to the same wireless network, they can communicate with each other, but if an STA that does not belong to a particular wireless LAN, then that STA is not allowed to join in the wireless, to join in that LAN. So basically, if you are using Wi-Fi network, then of course you use an AP, and which can define a wireless LAN, and of course you need to sign up. So the STA needs to be given some sort of authentication. So if an STA belongs to this WLAN, then they can go into the LAN, and every STA in this WLAN can communicate with each other. If some other STA that does not belong to this WLAN, or that is not allowed to connect to this particular AP, then of course they have no, that STA should have no way to communicate the STAs in that connected to that AP. So this is what it means by wired equivalent privacy. So you just want to, the purpose was to provide an environment that looks like a wired environment. Okay, so if you think of a wired network environment, of course you have to, your device has to be hooked up to that LAN, to that network, in order to use that network. So this is wireless. I mean, so that you still should have some kind of mechanism to hook up to this wireless network. Okay, so that's really what that means, what this means. Okay, so WEP was published in 1999, which is the security component at the data link layer of 802.11b. The requirements of WEP is that all STAs and APs in the same WLAN have to share the same secret key K. Okay, so they all share the same key, secret key K, and that K is called the WEP key. And the length of WEP key at the very beginning was 40 bits, and then later it was extended to a longer bits, and the most common was 104 bits, and of course it could also be 232 bits long. WLAN devices may share multiple WEP keys identified by a 1-byte key ID. So this means that an STA can sign up to more than one WLANs. So because for this particular LAN, you use this WEP key. For that WLAN, you use another WEP key. So you do need for each key, you do need a key ID, okay? And, oops, sorry. And WEP keys are often selected by administrator. Okay, so in early days, when you got or bought an STA, they will need so this SIM card. They have to put this W key into the SIM card. They need to set that one up. Okay, so once installed, WEP keys will not change. Okay, so since WEP is to provide a wired equivalent privacy, so of course it needs authentication. So this is device authentication and access control. WEP uses a simple challenge response authentication mechanism. In particular, to get access to an AP, an STA does the following. First, it sends out a request. So STA sends a request for connection to the AP. Of course, you need to send out a request using this AP's SSID. And then this AP, upon receiving this request, generates a challenge, okay? That challenge is a 128-bit pseudo-random string, let's call it CHA, and sends it to STA. So STA sends a request and then receives a 128-bit pseudo-random string, CHA, so it has 16 bytes, okay? So each A sub I is a byte. Okay, and then STA needs to send back a response to the AP. So what STA does is to generate a 24-bit initial vector V and encrypts CHA using the WEP key, okay, shared between AP and STA. So as we mentioned in the previous slide, all STA belongs to the same WLAN, which of course belongs to the same AP, are given a WEP key, okay? So the underlying authentication, the underlying encryption for STAs is ARC4. So this is encryption. This is a lightweight stream cipher. So this is encryption. So that WEP key, K, hence is also called ARC4 key. So in this response, it generates this, it generates the initial vector, okay, and then this K is the WEP key, and then for ARC4, the key is V followed by K. So this is offset concatenation. So this ARC4 key indicates this key is only used for this particular section. So for this V, okay? And the response, this STA sends back to AP is the following. So it has the initial vector followed by 16 bytes, also 128-bit string. But each of these RI is A sub I from the challenge string, exclusive or KI. So KI is the ith bit of the WEP key. Okay, I is from 1 to 16. So upon after receiving this response, the AP will verify whether this STA does indeed have this WEP key K. So AP applies ARC4 on this key. So ARC4 basically just take this key as input and generate a sequence of subkeys, okay, which is, so this is the sequence of subkeys, okay, generates from this this ARC4 key. So it generates the same subkeys, and then, so then you get you get K sub 1 up to K sub 16, which is the subkeys generated by ARC4 on this ARC4 key. So since you do have the same KI, and you do this exclusive OR with RI, you get a result A sub I prime, which should be the same as AI if STA has the same key K, okay, with with the AP. Okay, so that's a verification. So after this is done, then this particular STA, if verified, then is allowed to connect to AP. Okay, so this is access control. And then next part for WEP is data integrity check. Okay, the goal is to ensure that packets are not modified or injected by non-legitimate STAs. You want to make sure that in this particular network, okay, all the packets between these STAs have not been modified or injected by non-legitimate STAs, by STAs who do not belong to this particular AP. So for this purpose, WEP uses this is CRC32 value of M as its integrity check value. Okay, so this is a common CRC32 is a common network technique to detect transmission errors. Okay, so the reason for using CRC32 is because it has simple algorithm for verification. Okay, so it can be then easily implemented on a chip. So to get a k-bit CRC value, let's say this is a M, which is a M-bit binary string. You think of this is a input string, and P is a binary polynomial of degree K, which can be represented as a K+1 bit binary string. So this is k-bit CRC value is obtained by dividing M. So this is M followed by 0, K copies of 0. So you divide this string by P. P is a polynomial. And to obtain a k-bit remainder, and that remainder is called CRC of M. So if you pick K to be 32, then you get this CRC32 value. And if M followed by this CRC of M is not divisible by P, then it implies that M has been modified. So this is for error detection. So if something goes wrong, then it's not divisible by P. Then of course you know that M during transmission there is an error, or in general it can be used to detect whether this M has been modified. Okay, so what we need to know here is that CRC32 is a algorithm that's easy to verify whether this particular string is divisible by P or not. And it can be built on a chip. It can be implemented on a chip, hence it has a fast speed to be carried out. All right, so next, let's look at encryption. So since this works at the data link layer, and so what you are having is a frame. So let's call this LLC frame. So the encryption is done following the following steps. Okay, again, it is at the MAC layer, sublayer, and the purpose is to encrypt an LLC frame. Okay. All right, so let M be an LLC frame. So you get M, and then followed by a ICV, integrity check value, which is a CRC32 of M. Let's call it a string of M sub 1, M sub 2, up to M sub L. So then the STA, which is the sender, first generates a 24-bit initialization vector, V, okay, as we said earlier, then uses arg4 on this input. Now again, K is a shared WEP key between an STA and an AP, between a legitimate STA and the AP it belongs to. Okay, so then arg4 on this input generates a sequence of 8-bit subkeys. We call it K1, K sub 1, up K sub 1, K sub 2, blah, blah, blah. So then what you do is to encrypt this by doing the exclusive OR of M sub I with K sub I. So what you do is you keep generating this sequence subkeys. So you need L subkeys. So that you get, from that you get a ciphertext byte, CI. Then the sender, the STA, okay, so MAC sublayer adds a header to the payload, okay. So this is the payload. You'll need to send over the initial vector, initialization vector, which indicates this this packet is for this particular encryption, okay, and the key ID to get to this particular key, and this encrypted frame, C1 up to CL. Okay, so this is the encrypted LLC frame. And so the general form of this encryption becomes this. Okay, so this is the frame, original frame. And this is a sequence of subkeys generated by ARC4. And then it just looks like this. Okay, so this is the data part, M. Okay, so this is M. And integrity check value of M, which is a CRC 32, sub 32 of M. And then you put the key ID, so WEP key, a WEP key, and the initial vector. Okay, so, and then it puts a header, AO2.11b header. Okay. So that is the authentication and encryption. Okay, so so let's pause a moment and think it through. So first, okay, in order to have a wired equivalent access, you use authentication. So only legitimate STAs are allowed to be connected to this this AP, so which is equivalent to hooking up a device to a wired network. And then only the devices belong to the same network can see each other's packets, just like Ethernet, right? So Ethernet is a broadcasting network. Each station broadcasts a packet, and every other station can see that packet. But no STAs outside this particular network can see these packets. Can see the contents of these packets. So this is done by encryption. Okay. So so each packet is encrypted using a shared secret key amongst all STAs and AP. Okay, so if an STA does not belong to this AP, it does not have this key, so that means it cannot decrypt the message, the packets. Okay, so now we know we do have some sort of wired equivalent effects using WEP. So it was used from 1999 to early 2000 until people found a lot of problems or security flaws of WEP, and WEP actually failed miserably. Okay. So this is actually a very good example to learn that network security protocol can the security of any protocol, any security protocol for a product needs to be tested out. This WEP was not tested out thoroughly. Okay, so but anyway, so let's look at the security flaws of WEP. So the first flaw is on authentication flaw. So as we saw earlier, WEP uses a challenge response mechanism to authenticate an STA. So this challenge response authentication scheme is vulnerable to the known plaintext attack because of the exclusive OR operation. So that is so as we can see here, this is simply a simple exclusive OR. Okay, so if you know a plaintext, no plaintext, you then you can learn these subkeys. Okay, so now this is an example. Suppose the attacker malice can intercept the challenge response pair. So we get one pair, char, and so this is sent from the AP to an STA, and this is sent back to the AP from that STA. Okay, and then the attacker calculates. Okay, so CI, C sub I exclusive for R sub I. So the C sub I is from char. Okay, the i's byte of char. So then you get KI. Then she sends a request to the AP and waits for challenge string. Okay, so this is a non-legitimate STA. Okay, so malice is non-legitimate. So she sends a request for connection and waits for challenge string. So she's supposed to get another challenge string called char prime. She then generates the response message, okay, using the keys. So using these keys and sends RES prime and the previously captured initial vector V to AP. Okay, so initialization vector, because the subkeys are generated using arc4 on V concatenate K. K is the WEP subkey. Okay, so according to the WEP protocol, AP applies arc4 to V concatenating K, generates the same subkey streams, K1 up to K16. So then, of course, what is needed is for the attacker to get this pair, okay, which includes an initial vector. Okay. So you should also get this initial vector for this particular KI. So get the initial vector, because initial vector is sent. We'll go back here. Initial vector is sent in plain text, right, in the response, V, and then R1 up to R16. So the initial vector from here. So then it generates the same sequence of subkeys. Then obviously you can verify this to be true, and hence malice STA now authenticates herself to AP that it is legitimate. Okay. So it fails really miserably. The next security flaws of WEP is integrity check flaws. So using CRC has the following weaknesses. One, CRC is linear, which is good. It is easy for computation, but however, when you want to use it as a ICV, then it's not that good. So it's linear because CRC of exclusive or Y is equal to CRC of X exclusive or CRC of Y. So this linearity allows the attacker to modify a message without changing its CRC. So which means that the attacker can use a captured CRC for a different message. So CRC here, another weakness is that CRC does not use secret keys, which allows the attacker to inject new messages and tricks AP to believe that injecting message is legitimate. Okay, so for the following purpose: tampering, injection, and fragmentation attacks. Now let's see how message tampering is done. So Alice sends to Bob. So assuming Alice and Bob are legitimate STAs. So Alice sends to Bob the following packet. Okay, so as we said earlier, so this M is the original message. You have is CRC integrity check value of M. Of course, the purpose, once again, of using it is to make sure this M has not been tampered with, okay, or has not been modified. And then the encryption is done by exclusive OR ARC4 on this key, okay, so you get this. Say the attacker malice intercepts C and modifies C as follows, with a desired new string gamma. So this gamma is a new packet, okay, the content of a new packet. So this is what does a C prime looks like. So this is a new, of course, because she knows this gamma, she can compute CRC32 of gamma because it doesn't need any secret key. So this is easy to compute. And then whatever she intercepts here, that's a C, you do exclusive OR of C. So then Bob receives a new message, M prime, which is a gamma exclusive OR M with the correct ICV of CRC32 of M prime. Okay, oops. So that means you can use this is the CRC value, all right, even though you don't know M because it has been encrypted. But then you get a new message, M prime, and you can compute a CRC32 M prime in the encryption setting. So this is shows why this is true. So we put this in here. gamma concatenating CRC32 gamma exclusive OR C. So you write down, so C is equal to this. So you put that thing over here. So what you get is this by copying this down. All right. So exclusive OR is a so this is a new string. This is a new string. This is a new string. So the exclusive OR actually is gamma and M, followed by this CRC32 of gamma, exclusive OR CRC32 of M, and then exclusive OR this. Okay, so this is equal. And we know it is linear. CRC32 is linear. So these two is equal to this that we saw earlier. You copy this down. So finally, so you'll get, this is M prime. This is M prime. And you have exclusive OR. So this is encrypted form. Okay. So that means you can tamper with a packet and without being detected. So how do you inject a message? So this is how it can be done. So suppose M comma C is known. Okay, so this is the origin. There's a known plain text. So you have an M, you have this corresponding ciphertext is known. And V is the initialization vector for generating this C. So suppose you know MC, you also know V that is used for generating C. Then you do M exclusive OR C, which use the key stream of encrypting M, right? So you use the sequence of substrings. So you have that. But of course, that generates using this particular initial vector V. So now let's say that any message the attacker malice wants to inject to the network and fools or tricks AP and the STAs to believe that this SATA is legitimate packet. Now remember, V is transmitted in plain text. So what malice needs to do is to compute CRC32 of SATA and then injects. Okay, so it has this initial vector. So so SATA is what she wants to inject to the network. And you attach CRC32 of SATA and attach these ARC4 V containing a K. Now remember, this is obtained by doing this operation. Okay, so then you get that. So that means what malice needs to do is to wait for this particular vector, initial vector, to be reused to inject that packet, inject this packet. And this packet now will be considered legitimate by the AP and other STAs. And we know that this initial vector is only 24 bits. So 2 to the 24 is a small number. So you don't have to wait for too long to see that V being repeated. Okay, so this is how a packet can be injected. Next is a fragmentation attack. So this fragmentation attack takes advantage of LLC frame header to inject new messages. So in particular, so this is really hardware dependent. In particular, LLC frame has 8 fixed values. So it's a fixed, so no matter what packets, they always have these 8 fixed values. So attacker obtains these 8 subkeys using exclusive OR. So because something is always known, okay, is because they're fixed. So you can at least get 8 subkeys, okay? So you get the subkeys. So then attackers' tricks are following. So attacker malice injects 64-byte LLC by segmenting the LLC frame up to 16 segments into 4-byte fragment, okay? And then use V and the subkey stream K1 up to K8 because these are known, okay? So these you can do exclusive OR to get them to encrypt 4-byte frames, okay? And the 4-byte integrity check value. Put it to a MAC frame and inject it to the network, okay? So you can inject a bunch of very short packets of frames, actually frames, because it's at the data link layer into the network, okay? So what I said earlier, when I said packets, it should all be frames, okay? So because we are at the data link layer. Okay, so we have the following other security flaws of WEP. It's a confidentiality flaw. So this has to do with encryption. Encryption, ARC4 encryption is weak, okay? As long as a initial vector occurs again, right? So your first captures a ARC4, the key subsequence. You capture some C, known plain text attack. So so just like we said earlier, so you just need to wait for this same initial vector to appear again. Then you can compute. You can use this initial vector and to decrypt. To when the initial vector appears, you already have the same sets of subkeys K1 up to K sub L. And then you can use that to decrypt that particular frame, okay? So 24-bit IV is not too big, right? So you have this many, but of course using birthday paradox, the probability a particular IVV reoccurs with a probability greater than 1, you only need to see about this many frames, 5,000, a bit over 5,000 frames. So of course, this will happen very quickly. So, and then there are other issues on ARC4. So this is ARC4 weak keys. WEP keys can often be learned from weak initial vectors. Okay, there's quite a bit of a study on this. So a number of web cracking software tools. There are a number of web cracking software tools available on the internet, okay, which are based on the fragmentation attack, or FMS attack. All right, so that is the story of WEP. Okay, so WEP was used, but the security of WEP is weak. Okay, so that means we need to fix it. Okay, so in the next video, we're going to talk about how to fix this problem.